So we've just defined the concept of a basis of a vector space. A basis is a list of vectors in your space that spans the space and is linearly independent. Now, when we work with vector spaces, we typically want to work with one of the four fundamental subspaces of a matrix. So the question now is, how could we numerically construct a basis for a given fundamental subspace? And it turns out we can do this sometimes in multiple different ways. So this theorem says that we may systematically construct bases of each of the four fundamental subspaces. Let's start with the column space of a matrix. So the first part of this theorem is giving us two different ways we can construct a basis of the column space of any matrix. This first line here is telling us that we could get a basis by looking at the pivot columns of our matrix. The second equality here is saying another way we could get a basis is by looking at the non-zero rows of the reduced row echelon form of the transpose of our matrix. Both of these will give valid bases for the column space of a matrix. Note that these will give different bases, but they're both valid. Well, if we understand the column space of a matrix, the theory is the same for the column space of the transpose, except I have to replace all of the A's with their transpose. So if I want a basis for the row space of a matrix, that's the column space of the transpose, one way to do it would be to look at the pivot columns of the transpose of my matrix. And another way to do it is to look at the non-zero rows of the reduced row echelon form of my matrix. Both will give valid bases, but in general, those will be different bases. What about the null space? Well, in the example we just did in the previous section, we saw that if we use the reduced row echelon form of a matrix to write the dependent variables in terms of the free, and then write the general solution to v equals 0 as a linear combination of vectors, we called the vectors that popped out of that process the pivot solutions to av equals 0. And it turns out that the pivot solutions to av equals the 0 vector always give you a basis of the null space of a matrix. So to find a basis for the null space, we just row reduce the matrix, write the dependent in terms of the free variables, and then look at the pivot solutions as a list of vectors, and that will give a basis. And of course, studying the null space of the transpose, so the left null space of a matrix, is the same thing, except I'm no longer studying A times V equals the 0 vector. I'm studying A transpose times V equals the 0 vector. So if I want a basis for the left null space, I need to row reduce the transpose of my matrix and look at the equation A transpose times V equals the 0 vector, write the dependent variables in that system in terms of the free, and then look at the pivot solutions that pop out of that process. So this one slide gives us a systematic way to construct at least one basis per fundamental subspace. And for the column space and the row space, we actually have two strategies here. So let's look at an example where we construct all of these bases. So here what we're given are calculations where we take a matrix A, and then we row reduce it. And then I'm also row reducing the transpose of A. With this data, I can construct all of the bases we just mentioned on the previous slide. So what can we say about this particular matrix? Well, for this particular matrix, what I'm studying is a 3 by 4 matrix. So I can look at all of these various bases. The first basis will be for the column space, and the first strategy said we could choose just the pivot columns of our matrix. So the pivot columns of our matrix are the first two columns of our matrix, because we see that the pivots are in the first two columns when we row reduce. So this gives us the basis -2, 3, -1, and -7, 10, -2 as a basis for the column space. The second strategy for finding a basis for the column space says instead of looking at the pivot columns of our matrix, we could instead look at the non-zero rows of the reduced row echelon form of the transpose of our matrix. So now we want to look at the two non-zero rows for this example of the reduced row echelon form of the transpose of our matrix. That would give us the list of vectors 1, 0, -4, and 0, 1, -3. So here we found two different bases for the same vector space. The column space of this matrix, on one hand, is the span of -2, 3, -1, and -7, 10, -2. And on the other hand, it's also the span of 1, 0, -4, and 0, 1, -3. Both of these are valid bases of the column space of our matrix. If we go to the other side, we can apply the same principles, except now we exchange the roles of A and A transpose. Our first strategy says we can look at the pivot columns of A transpose. Well, according to our data here, that's just the first two columns of A transpose, which is really the same as the first two rows of A. So those are the vectors -2, -7, -4, -9, and 3, 10, 6, 13. Our second strategy says we can look at the non-zero rows of the reduced row echelon form of the original matrix. So those would be the two non-zero rows of the reduced row echelon form of A. 1, 0, 2, 1, and 0, 1, 0, 1. This gives us two valid bases of the row space of our matrix, which is the column space of the transpose. Again, different bases, but both equally valid. What about the null space of our matrix? For the null space, we said we can look at the pivot solutions to AV equals the zero vector. So how are we going to do that? Well, we look at the equation AV equals the zero vector, and we row reduce it. So we're interested in the reduced row echelon form of A now, and we want to write the dependent variables in terms of the free variables. So here we see that we'll have two dependent variables and two free variables. When we write out the generic solution to AV equals 0 using this method, we'll find that all of the solutions are the linear combinations of -2, 0, 1, 0, and -1, -1, 0, 1. Finally, for a basis of the left null space, so the null space of the transpose, we want to look at the equation A transpose times V equals the zero vector, and write the general solution as a linear combination of the pivot solutions. So here we're looking at the reduced row echelon form of the transpose. Here we see that we will have only one free variable, and when we write the dependent variables in terms of the free variable here, we'll get a generic solution as a linear combination of just one vector, and that vector will be the vector 4, 3, 1. So this is all 6 of the bases we've explicitly described for the 4 fundamental subspaces. We got 2 bases for the column space, 2 bases for the row space, 1 basis for the null space, and 1 basis for the left null space. So again, this is a systematic procedure by which we can find bases for all 4 of the fundamental subspaces.